This is my talk for Parallelizing the C++ standard template library. A little bit about myself first. My name is Grant Mercer. I'm currently a second-year student at the University of Nevada, Las Vegas. I'm pursuing a bachelor's degree in Bachelor's of Computer Science. And last summer, I worked at the Stellar Research Group. And while working at the Stellar Research Group, I primarily worked on implementing standards proposal N4352, which is a technical specification for extensions for parallelism. And it's going to be the primary point of this talk today in parallelizing the STL. I want to put in some background information first because I implemented this proposal inside of HPX. And HPX is a general purpose C++ runtime system for parallel and distributed applications of any scale. It enables programmers to write fully asynchronous code using hundreds of millions of threads. And it's the first open source implementation of ParallelX. ParallelX is an execution model which aims to overcome the four main barriers of what's holding parallelism back right now, which is starvation, latencies, overhead, and waiting. I guess that's a repeat at the bottom. The focus points of this talk that I want to try and get through are the reasons why we should have a parallel STL, our experience implementing these at HPX, the results we collected from benchmarking so far, and some pros versus cons of why there might be some problems with this proposal, as well as why it might be a good idea. So to begin, why should we parallelize the STL? Well, parallelism is here to stay. There's no doubt that frequency scaling is a thing of the past. At the end, during, I believe, the year 2004 was when Intel officially switched from their architecture of frequency scaling into parallelism. And since then, it's only grown. We were seeing newer and newer languages such as Go, Swift, Rust, Nim, all putting parallelism in their core functionality in their libraries. And it'd be pretty cool if C++ could actually keep up with these languages and also put some parallelism in their own libraries, especially with the STL, such a widely used library. It could also build some widespread existing practice for C++ parallelism. And it's going to offer a ton of scalable performance gains and user flexibility for any of those who want to choose to use the STL in their program. Now, standards proposal N4352 is the technical specification which outlines how we would go about accomplishing a parallel STL. And in this document, it talks about any of the new requirements, any of the new details that would go into this library, as well as defining a new list of the algorithms that would be parallel. Because not all the algorithms inside of the STL can be parallelized initially. You have something like accumulate, for example, which the first value depends on the previous value, so therefore it cannot actually be parallelized. Here's a list of all the proposed algorithms that the TS defines. So you have a really broad range, anything from copy to sort to rotate, search. There's a lot of algorithms that can now be parallelized. It's aimed for acceptance into the C++ 17. Our implementation at HPX takes advantage of C++ 11, which has turned out to be really useful for us, especially with the use of lambda functions and a couple other C++ 11 techniques. The TS currently lies in the standard parallel experimental V1 namespace, which is a bit of a mouthful. But once it's standardized, they're hoping to, just as the previous STL, lay in the standard namespace. Our implementation at HPX lies in the HPX parallel namespace. So the new thing with these algorithms is that there are no new requirements, which is one of the biggest things about the proposal. Is currently all the requirements, everything you'll see on CPP reference or any other document site for these STL algorithms will remain the same. There are no new iterator requirements or arguments. The arguments will not change currently from what they are. But one new thing that will arise is an execution policy. So this is the one new argument that the STL brings. And it's an object of an execution policy type indicates the kinds of parallelism allowed in the execution and the consequent requirements on the element access functions. So what this means is that you're essentially passing in a tag so the algorithm knows which kind of execution to apply to that algorithm, whether it be sequential, parallel, or parallel vectorized, which allows multiple elements to be executed at the same time for parallel vectorized. But I won't be talking about parvec as much. I'll be focusing on sequential and parallel. Here's an example of what you would do with this new TS if it were to become standard in C++ 17. At the top you have your usual int, vector, v, and your standard sequential sort, where you would sort from beginning to end from the vector. And now if you take advantage of the parallel execution policy, you have your using namespace hpx parallel, so you're in our runtime system. You can either sort it sequentially by passing in the seq tag in the beginning, or you can permit a parallel execution, which is passing in par. And what's really cool is that you don't need to decide whether you are sequential or parallel during compile time. This can be completely a runtime dependent thing. So if you have a piece of data that's expanding at some rate and you only want to parallelize it after a certain amount of elements have been reached or a certain condition has been met, then you can create a threshold. You can create a blank execution policy object, initially set it to sequential, and if your threshold or your condition is met, then you can start parallelizing your function when you choose. Yes?
Is parvec superset of par? Why would I choose par over parvec?
So the question was, why would you choose parvec over par, or par over parvec? And parvec is created to disambiguate the types of parallelism allowed, where under my impression, I'm by no means a compiler expert, I believe that vectorization is already a key part of optimization, so, which is why I won't be talking about parvec much. But in case you have some compiler and you don't want to actually allow, or if it doesn't initially allow vectorization, you might not want to pass in parvec if you don't want it to for some reason. Yeah. Some things to note about the par tag is that it's the caller's job to ensure data correctness. So data races and deadlocks are not the algorithm's job to detect and find. It's as if you were writing your own parallel algorithm. If you have bad code, your code's still going to crash. It's still going to have undefined behavior. Here's an example of a simple what not to do with these new algorithms. If you're trying to push back multiple items inside of a vector at the same time, just as before, it's not going to work. You're going to get either a crash or undefined behavior. There's no smart checking. There's no ease of doing that. So just because you type par also, it doesn't mean you're guaranteed a parallel execution. It means it's permitting the algorithm to run in a parallel fashion. This is because of input iterators, where, as I mentioned before, there's no new requirements placed on the algorithms. So in the case of input iterators, where you can only achieve the value once and you can't jump ahead inside these iterations, it can't be parallelized. So in the case that you pass an input iterator in and you also pass in a par tag, it will detect that you're using input iterators and it will run the sequential version instead. We could have done an error, but it also takes away from the proposal's idea that there shouldn't be any new things to worry about with your requirements on iterators. So it wants to keep it as contingent as possible, where there's no new bounds to meet. Some important things about exception reporting behavior in the standard is that if you don't have enough temporary resources required and none are available, it will throw a standard bad alloc. And in the invocation of the element access functions, if an exception occurs, it will catch all exceptions in that loop inside of an exception list and then afterwards throw the exception list. And in the case of sequential, it will actually also throw an exception list. So it's sort of to, yes?
Is there any way to alter that behavior and have it throw the first exception?
The question was there any way to alter that behavior and have it throw the first exception? Not currently. Currently it is just everything is stored in an exception list and thrown afterwards. Now at HPX, I don't know if any of you attended the talk yesterday, but HPX is very key on asynchronous executions, and we decided to add an additional policy for our own runtime system called the task policy. And what the task policy does is it allows us to return a future of the result and then return and join the program whenever we want. So it takes away from the fork join kind of thing of parallel, and it allows us to then, if we have a lot of work we need to send off for a sort, we can do some work after that, and we can choose to join after. So you're getting even more flexibility in your code, and you can choose when you actually want to join the data, and you can also start doing data flow and combining tasks. So in the initial parallel design of these algorithms, they all take a range, and this range needs to be partitioned up, and some sort of algorithm needs to be executed on each partition in order for us to actually implement the algorithm. So we used a couple of different classes at HPX, and we called those partitioners. So our first partitioner of how we implemented these algorithms is we called it the for each partitioner. It's the simplest of all of them. What it does is it simply takes a set of data. It will divide that data into an equal chunk size based on the amount of cores available in your computer, and invoke a passed function on each subset of that data. It's mainly used in the algorithms such as for each and fill, where the return result of each function invoked on the subset is not actually needed. So in a quick example, if you have a set of 12 elements and you had 4 cores, for example, it would break up the data set into 3 equal chunks and invoke a function f passed into the partition on each chunk. This is how we implemented for each n. We have our template parameters, our execution policy, and the function passed into it, and the return result right below it. And the reason it's called parallel is because it's actually wrapped inside of a structure, and inside that structure, when you actually call the algorithm, that's when it'll decide whether you can actually permit parallel execution, whether there's input iterators, it'll call sequential, it'll call this function if parallel execution is possible, and you pass in the tag. So right here is where we're actually calling the partitioner. We're forwarding any of our arguments we need, as well as our f, and this lambda function right here is what will be executed on each subset. So inside each subset, we're looping through, and we're applying the function f to that subset. Simple. Now nextly, we created the partitioner. It's similar to the for each, but the result of the invocation of each subset on those chunks is then stored in a vector, and a second function passed in will be executed on that vector. So this is how we ended up accomplishing algorithms such as copy, find, and search inside the parallel STL, where if you have 12 elements as before, and you were to partition that data up, invoke a function f on each partition, and then store the result inside of the vector v, and finally invoke a second function passed into the partitioner on that vector. So this is a 2-step process where you can then do an additional step. So with reduce, you call your partitioner and you forward your arguments, and in your lambda function, which will be applied to each chunk, you'll accumulate that partition, and then the second step will accumulate the accumulations of all those partitions. So that's where you need the result of each partition is then stored inside a structure or a data set, and then you can then invoke an additional function on that set. The reason I showed reduce was because we had an interesting problem in that one of our coworkers at HPX came up to us one day, and she was writing a benchmark, and she needed to compute the dot product of 2 arrays of x and y values. And she wanted to use our parallel algorithm since she was using HPX. And we thought this would be a great idea, and we had just finished reduce, so we thought, okay, well, reduce, you can do this with accumulate really easily, so it should also be the case with reduce. But what we found out is there's no, as you can see here with the implementation we have, there's no conversion function you can place on the iterator. So your initial value is actually constrained to what you're passing inside of the algorithm. So when we tried to write reduce for her, we found out that, say for this example down here, this is a generalized example. If you have a structure of points, and inside each structure is an x and y value, when you dereference one of those iterators, you're going to get a struct. So we had to create our initial value as a struct. And then additionally, inside that function where we compute the dot product, we then had to pass in a struct and return a struct. And our return result was only in the first element of that struct. And it was horribly hacky, a terrible solution. So we decided to write a proposal, 4167, which included transform reduce into the library. And this was eventually added. This was actually our specific example at HPX of how we returned reduce. Since we had two arrays, we zipped them together into a tuple, and therefore we were constrained as our initial value had to be a tuple. And then inside our actual function, we had to do some hacky solution of multiplying the two sides of the tuple together to make sure we don't actually multiply out into 0. But with transform reduce, what that allows you to do is it allows you to apply an additional function and take an intermediate step before you accumulate your results. So with the addition of transform reduce, and what you can use this algorithm for, we call the partitioner as usual, but inside this first step, we're now setting the initial value of each partition to the result of the convert function placed on that dereferenced iterator. So then you can then accumulate everything else while applying that function, and as before, accumulate every step of that chunk. And this is the entire code for the transform reduce, which just makes it so much more intuitive and so much more simple when you're doing the dot product. So if you have, as she had in her issue, two vectors of x and y values, you filled them with some random value, and inside here you can actually now put your initial value as a double, which is great. You're not wasting memory, you're not wasting space by putting in some arbitrary struct. You still have your tuple of the iterators of x and y values, but inside, this is your conversion function now. So this function, where it takes a tuple, will be applied to right here. So it'll convert the dot product and return that in the form of a double, and you simply add up that double, which is the standard plus function applied to the bottom. Now after that, we had one more partitioner we were using right now called the scan partitioner. And this one is the most complex of the three. And what it does is it has a three-step process. So the first step partitions the elements as the other two do. The second step invokes a function on the current partition and the leftmost partition when it's ready. So it's not the entire list. And then the third function is invoked on the resultant of all the step 2 functions. And this was useful for us in implementing copy if and inclusive and exclusive scan. So say we have a array of 12 elements again. We would partition that data up. We would then set the vector v sub 0 on, say this is the current partition. Once this is ready and the leftmost is ready, the vector v sub 0 will be the resultant of the functions invoked on those and returned by those. And that will be stored in an additional structure. And the function g, the second function, will be applied to that vector. So say the partition now moves to the rightmost one. So when that one is ready, and its leftmost one is ready, v sub 1 will be equal to those results, and the function g will be invoked on that vector. And then the third step invokes a final function and takes r as an argument. So copy if is an interesting example when you're writing parallel algorithms, because in the case of copy and copy n, these were very simple to write for us. This was almost just a simple for each and place something inside. And we attempted to solve the same problem with copy if, and we ran into a horrible bug when we actually tested our code, in that if you have an array of 8 elements and your resultant array where you want to place all of the values that are equal to 1, and you call a standard copy if, and inside our implementation all we did was actually copy the value over if the predicate was true. But what you end up having is you have these blank spaces in between, because you're not actually squashing the array or the structure together when you're just copying over. So what we needed to do is we wrote the scan partitioner in order to accomplish things like these, where you need to take an intermediate step and squash the array together once they finish up. So in the case of copy if, we use the scan partitioner. It's not the entire code because it's a little longer, but we're forwarding any arguments. And the zip iterator of first and flags.get, flags is actually a shared array which we will use to mark and flag any elements that are to be copied. So in our initial step, which will be partitioning every element and applying the function f on it, we'll flag any elements to be copied. In our second step, which will be ready once the current and leftmost are done, it will determine the distance to advance the destination iterator. And on the third step, which is the final step, which will be called on the resultant of all of these, it will copy the elements into destination in parallel. So this one in itself actually invokes the partitioner call. So it's that was our solution to copy if. This is also a similar solution to scan as well. Now, also when we were designing these parallel algorithms, we realized some were simple to implement, others not so much in the case of copy if in comparison to copy. We wanted to start simple and work up the grapevine and try and see how far we could get and the tools we could use from learning on these simple algorithms to get into the more complex ones. And we realized that a lot of the algorithms are actually almost arbitrary to implement once you have simple algorithms such as for each. In the case of fill n, if you don't count the type def, fill n can be implemented in just one line when you're calling a for each parallel instead. And all you're doing inside this is your lambda function here will set the every value of the range to the value passed into fill. And the boost MPL false is a way of jumping straight to the parallel execution for each n. So this does not do any second checking. It'll actually go straight to the for each n algorithm and call the parallel. As of today in HPX, these are all the algorithms we've completed. We still have a bit of work to go because we've left the harder ones for last, such as sort, adjacent difference. We have some more, but hopefully by the end of the year we'll have the entire proposal implemented inside of HPX ready to use. We've already had some of our coworkers use these parallel algorithms and have great success with them. This is a short example of one of the quick tests we ran to actually measure these algorithms, because when we implemented them, we had gotten maybe 10 or 11 done, and we wanted to make sure we were on the right track in terms of implementing these. We wanted to make sure that the measurements that we got were actually going to match up with parallelism and speed up proportional to the number of cores. So here in the measure parallel for each function, we're simply calling parallel for each, and inside we're delaying each iteration by some past variable. So this allows us to modify the data size, the amount of delay per loop, the trunk size, so the actual how much work will be on each thread passing into parallel, as well as at the bottom here we're averaging out some test count amount of times in order to try and take out far outliers of the results. So we wanted to measure the sequential, parallel, and the task execution policies. We wanted to see how task would perform, because now when you can choose when to join, you can start overlapping your executions when you have many parallel executions that are in place. So if you have a lot of work that needs to be done and you need to execute maybe 3 or 4 times, you can actually send 2 off and then wait for the first one afterwards, which will allow you to not have to wait for the first one to finish before you can send the second one off. So for getting the most out of performance, here's a strong scaling graph example over here. We were more conscious about our grain size and how these algorithms would perform at some average grain size level, because the grain size is the amount of work that you can execute per thread. And one of the biggest problems with measuring your grain size is that if you don't put enough work on each thread, the overhead of creating threads and executing them in parallel becomes far too much, and you start seeing horrible execution times. But as you put too much work on each thread, you start seeing a sequential execution, because if you have 100,000 elements and you're putting 100,000 pieces of work on a thread, you're just going to see a sequential execution. So here's the hardware we used. The important part to get out of this is that we have 16 cores, so in a perfect world, we're going to see 16 times as fast. But this initially isn't the case with small sizes. So when we tested a 500 nanosecond delay per iteration on a vector size of 10,000, what we found is that the optimal grain size still only yielded us about 10 times as fast as the sequential execution, which we were missing at least 6 times more as fast as what we wanted. And we feel that was just, as well as the parallel overhead, that once your data size gets at a small enough level, it's just you're not going to see the perfect results. But as you go higher and you bump up your vector size to, say, 100,000, and say you have 1,000 nanoseconds of delay per iteration, now you start seeing really good scaling in terms of we're almost at 15 times as fast as the sequential execution. And on the left you see at the optimal grain size, which is about 100 pieces of work per thread, you're also seeing the execution time is exponentially going down. But it's also important to note that on the left side, if you don't have enough work per thread, you're going to see like absolutely abysmal execution times. So this is important in that it's very easy to accidentally kill yourself on execution time and run time if you're not careful of how much work you're putting on each thread. And then when we measured task, additionally, we measured this with overlapping. So this is sort of like pseudo-perfect result in that we're seeing 16 times as fast. But this is with the case of overlapping. So we'll send an execution off, we'll send another off, and then we'll wait for the first one afterwards. So we no longer have to join and wait after the first one. And over here you're seeing 16 times as fast compared to the parallel. So we actually really like the task because you have this sort of extra flexibility and you have more room for improving your code and getting better performance out of the algorithms. Another example of some of the measurements we gained was one of my coworkers, Martin. Over the course of my last summer working on HPX, he was also there and he was writing an OpenCL backend for HPX, which would take advantage of CPUs, GPUs, DSPs, FPGAs, and create highly portable code. And he used parallel for each in his code in order to group work items into packets in order for sending them off later. And here was a sort of simple version of how we use parallel for each. We would take a range and group the threads together. And he saw actually some awesome results in using simply just parallel for each, where in terms of microseconds, you're seeing really good speed up on the left side when you have 16 microseconds in your work items. So the results we collected from this were that parallel executions will give us performance proportional to the number of cores, while also taking into account the overhead that comes with creating these threads. But it does scale very well the higher your workload gets. Initially, it can be a little bit tough to gain the optimal performance out of it. You would have to tweak your grain size as well. But as you pass over into the larger data structures of 50,000, 100,000 elements, you're going to start seeing really good scaling. I wanted to point out like a simple example use case of particles where not all the performance gains have to be in terms of big business or large applications, just something simple as writing a particle simulator. So one of the simple OpenGL tutorials, if anyone's ever done OpenGL, is creating billboard particles that will simply spew from some location and disappear, create, and destroy. And the easiest way to draw this stream of particles is to sort them by their alpha and then draw them in order of their alpha values. Because as you see here, it might be hard to see, but there's this blocking occurring where you have alpha values that aren't sorted and they'll be drawn on top of each other and create this sort of disparity between not actually looking like they're clean and in form. So the loop in terms of drawing these particles would be you handle your events, you determine the next location of your particles, you sort your container, you fill your buffers, and you draw. So if you're dealing with particles, you're dealing with a lot of particles in terms of anywhere from 100,000 to hundreds of millions of particles. So in terms of sorting a container that could possibly have up to hundreds of thousands of elements to 1 million elements, and using a new parallel sort, this could be some huge performance boosts for us. But I also want to mention some cons of maybe this proposal. I know the proposal sounds great, but there's also some things you want to take into account in terms of this. And it's that one of the fundamental issues with this proposal is that there is no resource sharing. So each call to an algorithm will separately create the resources required to execute this in parallel. execute it, and then destroy those resources afterwards. So in the case of running many parallel algorithms close to each other, you're not going to be able to share those resources. But another argument is in the case that if you're creating some sort of resource sharing, some sort of parallel algorithm, and you really need to resource share, the STL probably isn't your first choice anyways. So I feel like this, while it's an issue you should think about, it's not necessarily needed for the use case that the TS is trying to actually achieve. Also, maximizing your performance does mean that you need to tweak your grain size and you need to know your execution times. So currently what our algorithms will do is they'll take the amount of work and they'll divide the amount of work by the amount of cores you have available. And while this is useful and it'll get you some great results, yes?
So there's no thread pool implicit behind this?
There is, but it's managed internally by HPX, and there's no way to explicitly tell that thread pool to save the resources and continue on. There's no data flow possible. So yeah, and the question was, so is there no thread pool? And the answer is there is, but it's managed internally, and there's no way to actually reach that from the algorithms. So as I was saying before, in order to actually get the maximum performance out of the algorithms, you will need to know your grain size, your optimal grain size, which means you need to know your execution times. And this might not always be possible in the case that you're writing a function which may have varying iteration delays per loop, or you might not be able to actually measure your execution time inside these loops. So it could potentially create an instance where you're actually getting worse performance if you don't know what you're doing and you're throwing in these parallel calls, which would be more noticeable in the newer C++ community where if they just see parallel algorithms, they initially try to parallelize every single thing. You're going to have terrible results if you're trying to parallelize a vector of 10 elements. So, conclusion, summing things up, the proposal, N4352, the TS for the parallel STL, has shown us some really promising results at HPX. I think it could bring a ton of user flexibility to C++ and really set the base and fundamentals for existing practices of parallelism in C++. I've included some information in case you guys wanted to check them out. My GitHub's at the top. There's the Stellar Research Group and the HPX repository also on GitHub. The Stellar Research site is that one, and this is the actual link to the proposal if you guys want to check that one out as well. Is there any questions?
Yeah, in many cases for reasonable size sets of data, where reasonable is like 10,000, the choice is not really sequential parallel, it's vectorized versus parallel. So have you guys looked at that at all? Because I noticed you didn't really mention vectorization in any of this, although there is a parvec.
At HPX, I don't believe we focused on parallel vectorized too much. Do you want to comment, Thomas?
Yeah, actually, vectorizing your code is kind of orthogonal to what we do with HPX, right? Because it seems to be a compiler problem, really, and the parvec is really just to hit the compiler to actually, if the compiler is not able to figure out that your loop body is able to be vectorizable due to data dependencies or whatever, you can explicitly say, hey, I know what I'm doing, just vectorize this damn thing, right? But it's more like an override to the compiler, the parvec, and it's really orthogonal to the whole business of concurrency.
I would sort of agree that if you've already parallelized something, then the compiler really can't vectorize at that point.
That statement is simply not true.
Yeah.
I mean, one, you're talking about bit level parallelism versus task level parallelism, but it's just not true that if you parallelized your code at the task level, that the compiler won't vectorize it. The compiler will always vectorize your code. It's very
No, I'm not saying it won't. I'm just saying it might be much better to have not parallelized it.
I think if you don't have a lot of work, if you have insufficient work to parallelize your problem, then that's true. But if you have insufficient work to parallelize your problem, then it's not a problem that needs to be solved with parallelism.
It's really two orthogonal problems.
Yeah.
Probably won't repeat that. Yes.
So you said the existing, for instance, the existing sort proposal for parallel does not return a future.
Mhm.
So that means that the caller is blocked until the work is complete.
Yeah, so
But your proposal, it returns a future.
Mhm.
So when is the actual work scheduled then? Is it at the time that the future is created, or is it when you block on that future?
Okay, so the question was, the normal parallel tag is blocked where it's fork join, and in terms of the task policy, when is the work actually scheduled, and when is it like returned?
Yeah. In other words, when you get that future, what do you know about the progress of that task,
Mhm.
just by virtue of holding on to the future?
So when you get the future, the work is scheduled when during the creation of the future, and you're not required to actually wait for that work until you call either future.wait or future.get. So the work will be asynchronously executing during the lifetime of that future, and once you call get or wait, if it hasn't finished by then, it will then wait for the execution to finish. So before that, it will be executing, but you're not required to wait for it until you actually explicitly declare that you want that value. Any other questions?
So the partitioning of work per thread is on a static basis. There's no dynamic allocation or work schema?
So the question was, during the partitioning, it's all done on a static basis. It takes advantage of HPX's internal system, so it is dynamic. Do you want to comment now, or I saw you shaking your head?
So actually, the chunk size is calculated dynamically. So you have two options: either pass a static or whatever you think is best in terms of chunk size, or the system automatically figures out by doing some test runs.
So the comment was you can either explicitly declare your chunk size, or the internal will actually automatically generate a chunk size, which currently divides the amount of work divided by your number of cores. Did you want to comment on that, Howard?
Yeah, no, it's actually just running a few elements with the user supply function, and then just checks how long that takes and
Mm-hmm.
divides based on the number.
Okay.
Yeah, so the initial guess is
Mm-hmm.
not of course.
All right. Any other questions?
Is there any mechanism to adjust the priorities?
That would deal with the internal side of HPX. At least in the algorithms and choices, there's no specific way to reach that through the algorithms. You can't call the priorities through that.
So there is a notion of priorities in HPX, but it's sort of exists at a lower level. I'm not sure whether you'd be able to access it in this interface, but we do have some notion of priority. But it's works in queues, so the priority is sort of level-based, not like you can't guarantee this thread will happen after this thread, but you can sort of say this thread is more important than this thread, and the scheduler will usually sort of get that level of thread before a lower level.
But that isn't in this proposal.
Right.
There's no support.
Oh, and to comment, the actual task feature is specific to HPX. It will not be included in the proposal. So this is something that we kind of have that's a benefit of using HPX over the actual proposal.
So yeah, the issue with setting priorities and partitioning your hardware resources will be addressed with executors actually. So then the user gets the ability to actually choose the priorities and run. So, but it's again a different issue that can be solved in general, independent of the algorithm.
The execution will be deterministic. If I run the program twice, the execution path is around the same.
So if I understand it correctly, if you run the algorithm twice, it will allocate the resources.
In the execution part, basically you have suppose that you generate 4 threads, always, the second part run always run the thread, 4 threads as well.
It will not share them, so there's no way to share the resources, but you can guarantee that if you run the same algorithm twice, you'll get the same results, in the very least. The question was, if you run one of the parallel algorithms twice, will they use the same resources? Is that?
Suppose, okay, the first time you run, you run as 3 threads.
Mhm.
The second time you run as 4 threads. In this case, the result may not be deterministic.
I think I understand, but I don't have the sufficient knowledge to answer your question. Sorry.
So I guess this is probably more of an HPX question than the STL
Mhm.
parallel implementation, but suppose that I wanted to actually go off and use this in a program.
Mhm.
Currently got code that's using OpenMP, TDP as well as some native threading. And I've got all these things, all these thread pools, and it's a pain in the ass trying to get them to like not step on each other's toes all the time.
Mhm.
Is there a way to kind of get into HPX and say, you know, and to at least interact with the thread pool in some way that I can make sure that I'm not oversubscribing?
The question was, is there any way to use HPX and sort of share in the thread pools of OpenMP and other structures?
I don't necessarily share, but at least in some way coordinate. the use.
Coordinate.
So I don't have TDB and HPX that both think, oh, I'm going to use all splitting cores on this machine.
Mm-hmm.
So I wouldn't recommend using TBV and HPX in the same executable. As far as OpenMP, we have a OpenMP implementation that basically goes to uses HPX as the backend, which is a work in progress. But I would think that you would want your code to either use TBV or HPX and not try to use them together.
So,
That would be nice.
Thomas?
This problem will be solvable with executors.
Right.
So, yeah, executors will solve the problem.
So the answer to all questions, I guess, is executors. But seriously, executors are the answer because they allow you to sort of encapsulate different, sort of execution policies for different groups of your different portions of your code, basically, different groups of threads.
So it sounds like you actually have more ability in HPX to control the parallelism threading than you use in TDB, which is pretty bare.
But I mean, more importantly, like the executors are really cool because you can basically use different schedulers for different parts of your application. And yeah, and so yes, you do sort of have more control with assistance for executors and something like TDB, which gives you no real way to control how it's, what the scheduler is under the hood.
Thank you.
All right, any other questions? All right, well, thank you for attending the talk, and that's all.